first shout out his new Hagaroma eraser. And he used it on my chalkboard in my office. It's like, okay, I'm chilling out 11 bucks. It's coming in the middle of the day. So welcome everybody to this balmy afternoon for Roman's talk. Just say a couple of words about Roman. Well, first off, as I said, we listen and we don't judge. Roman came to my attention a little over 2 years ago when Alexei Davidov emailed me and asked if it would be okay if he tried my graduate set theory class with no background. And I said, sure, what the heck. So I got my hooks in him, and I guess we worked together pretty closely over the past 2 years, looking at mathematical logic, kind of working through this past year axiomatic set theory in depth, and this past semester looking at the method of forcing, which he's going to talk a little bit about today. I guess Roman is going to graduate school to pursue a master's degree at Miami University, working with a friend of mine, Paul Larson. Congrats. He's been very nervous all day.
Okay.
He spent about an hour in my office after advanced calc.
You have anything else to clear up?
We listen and we don't judge. We're going to give him donuts at the end. All right.
Okay.
Take it away.
Well, thanks for the great introduction. So I definitely, just to start, I don't want to just like force you to sit here and listen to me talk for an hour straight. Like, please ask questions throughout. I'm going to try and make this very big picture. I'm not going to like burden you with a ton of notation, except for one portion. But yeah, I'll try and stop, but like, please don't hesitate to ask me questions if you don't understand something. I'm trying to make this as accessible as possible. Okay, so without further ado, I guess we'll start at the very, very beginning. The field we're kind of working in. So, set theory. Set theory is essentially the study of sets, which is kind of obvious, but it's collections, right? In math, a set is a collection of objects. In the notation we use, we just open with these curly braces and we separate elements by commas. So this is the set of A, B, and C. Order doesn't matter. I can order B, C, A, C, A, B, whatever I wanted. I will briefly show you a couple of symbols just so we have them. I'm not going to spend too much time on this. Again, notation heavy is not my worldview. I can name such things, so I'll just use A to abbreviate this. I can use this symbol to mean A is a member of big A. Another symbol I can use if I have a set which sits inside of another one. I can use the subset symbol, and this would be the set AB is a subset, is the word we use, of A. And this line at the bottom just implies that that can also be the entire set itself. So A is a subset of itself. I will also super briefly cover logical notation, like 30 seconds. You'll see symbols like this guy. This is our shorthand for the and symbol. This is the or symbol. This little backwards gun is not. What am I saying? Backwards E means there exists. And upside down A means for all. I think that's the bulk of it. I'll try and leave this up for as much of the chalkboard space as I can afford. Again, if something doesn't make sense later on, just ask me. But essentially, okay, the question is, what are we going to do? If we're going to just study these objects and these symbols, what are we trying to do? Well, the entire goal, not the entire goal, but the frontier of set theory when it was being created is we wanted to axiomatize mathematics. So what that means is we want to write down a set of statements that are strong enough to encompass everything you might want to prove for mathematics. So a list of rules, and from those rules, you can find calculus, geometry, differential equations, whatever you want. The axiom set we work with is called ZFC. I will actually show you the axioms really briefly. If you've never seen logical notation up until right now, this will look crazy. If you know a little bit of logical notation, okay, then just enjoy the ride if you want to review how to review. So the PowerPoint was secretly on the whole time. Let's quickly go over the ZFC axioms. This stands for Zermelo-Fraenkel with choice. We have the axiom of extensionality. This means that two sets are equal if they have the same elements. We have foundation. This one kind of just rules out weird situations like a set being a member of itself and ensures that good objects are in our mathematical universe. We have the axiom of pairing, which lets us take two sets and just glue them together into like a set of both of them. We have union, which is not necessarily the small union symbol you're used to, but if you have a set that has other sets inside of it, the union symbol can kind of like strip apart those sets within other sets and give you all the basic elements. We have the power set, or the power axiom. We will talk a lot about this more in a moment, so I'll come back to that. The axiom of infinity. We are granted a set with an infinite number of elements. Comprehension. We can define subsets based on properties we notice. Replacement. Don't worry about this one, this one's kind of crazy. The only thing I'll mention here is that this is multiple axioms, actually an infinite number of axioms bundled up into one. It just lets you replace objects within sets where it makes sense. And choice. Don't worry about this one either. I will also leave this up here, so I just gave you that for free. But I will keep this up for the rest of the talk if you're confused at any point. Yeah.
For pairing and union, what's the difference between those again? I missed it.
The pairing axiom just says if you have two sets x and y, the set of both of them exists, so both has objects inside of a set. If I have some set with like objects bundled up in other sets, I can take the big union and it gives me, it kind of strips away
I see.
objects inside of them. Okay.
Nested element.
Yeah, exactly. Good so far? Any questions? Okay, so if my claim that set theory is strong enough to do all of math, I guess it's reasonable that we would start with one of the most basic things in math, and that's what is a number, okay? So we'll start with the first number, which is not 1. We'll start with 0. We define 0 as the empty set. We have a special symbol for it, just like 0 and the line through it. And from this set, we're going to build the rest of our numbers. So the object for 1 is going to be the set of the empty set. The object for 2 is going to be the set of the empty set, and the set of the empty set. I kind of don't want to keep going because it gets ugly really fast. Yeah, so something like that, right? Maybe you see the pattern emerging, right? I want these numbers to represent some size of a collection. This 0 set has nothing inside of it. This set for 1 has 1 object inside of it. This object for 2 has 2 elements inside of it, 3 for 3, and we would keep going. And the general formula here is that for the next number, I will take the number that came before it and glue it together with the set of itself. So any single natural number we want to define, we essentially look at all the numbers that came before us and throw them in the bucket. Another way I can represent this is that 2 is a set of 0 and 1. That's all we're doing here is looking before us. Still good so far? Nothing too crazy? Okay. And our notion of comparing numbers stays the same. So we can say in normal math that 1 is less than 2. This analogy holds, but we use the membership symbol instead of the less than symbol. So I can say that 1 is a member of 2, and that would mean that the set of the empty set is a member of this guy, and that holds true. This object right here is inside of this set, and this will be the way that we define ordering on the natural numbers. Okay. Do you all remember the axiom of infinity that I brought up earlier? Okay, so we are granted the existence of infinite sets. And if you paid attention for the very brief amount of time that I had the axiom of infinity up here, it actually looks really similar to this process. It's kind of describing what this process looks like for all the natural numbers. So there is a set which at an intuitive level contains all the natural numbers we could ever want. And the special name that we will assign to the set is omega. So for my more math people in the audience, you can, I guess from now on, interchangeably think of omega as the natural numbers, the symbol n here. I might switch between them, they mean the exact same thing for our purposes here. We can also keep going, right? For all numbers that come next, I can call to this definition. So what would happen if we just applied this definition to omega, our first infinity, right? I can define omega plus 1 as omega union with omega. So it's kind of like the natural numbers with another object thrown on top. This preserves our ordering, because I could look inside omega plus 1 and see a copy of omega with my membership symbol, and this holds true. And so oftentimes in set theory textbooks, you'll just see this be written instead. So our notion of order holds true, that omega plus 1 is greater than omega or vice versa. Okay with that so far? Okay, we can take this pretty far, although I will need a little more space. So let me go over here and erase this guy. Without getting too much into details here, so we had our natural numbers, then they kind of approach a limit point. In fact, we call omega a limit, and I'll introduce the name for that more specifically in a minute. So we have omega. I already showed you we can define omega plus 1. Of course, omega plus 2 naturally follows. Well, I have the 0, 1, 2 pattern here leading to omega. I have plus 0, plus 1, plus 2. So we can extend this to omega plus omega, which you can also write as omega times 2. I can keep going, omega times 3, so on and so on. I need to destroy our natural numbers for a minute here. We will get eventually omega squared. We'll keep going, and we can get really crazy things like, huge powers of omega. You can kind of do whatever you want. It's, no rules here. But the thing to keep in mind here is that our ordering still holds. I can pick, this kind of pseudo number line I'm drawing here. I can pick out this guy. I can pick out this guy in that sense that one is contained and the other still holds. Are we okay with that concept? Okay. The name we actually assign to these guys are called ordinals. So it's kind of indexing an infinite process, and I'll talk about that more in a moment. All right, so I'm claiming that these sort of infinite ordinal numbers can help us to index a process in the sense that I can look at one and see where it comes before or after another. What's another thing that we use numbers for? You might want to describe the size, right? So with our natural numbers that I so beautifully erased just a moment ago, they correlated to sizes. So I can look at each set, I can count the number of elements in that set, and I can make a reasonable deduction that this set has 3 elements, 4 elements, 5, and do that for all the natural numbers. How do we compare sizes among infinite sets? This is the big question we want to answer here. And the way we do this is through a bijection. Don't worry about what that means if you haven't heard of it before. All we're doing here is we're pairing things up. So if I have some set with A, B, and C, another set of 1, 2, and 3, if I can kind of give each element a single pair and leave nobody out, I made a bijection. And this is a reasonable sense that this set and this set have the same size. So I can pair everything up really nicely. This breaks down a little bit when we get to the infinite stages. Let's take a classic example. Our natural numbers, which is also omega. So start counting here. let's take the even numbers. So the even numbers are 0, 2, 4, 6, and so on. I would play games and be like, oh, which one is more? But maybe you know what's coming here. There's a natural way that I can pair these up, right? In one sense, it kind of looks like I'm starting with this set and I'm taking a bunch of stuff away, right? I took away 1, I took away 3, I took away 5. But I can still biject between both of these sets. I can draw this nice pairing with my arrows. And because I can form a bijection based on the rule that n in the naturals gets sent to 2n, these sets actually have the same size. So in one sense, it looks like I took stuff away. They're actually the exact same size in our notion of bijection. And the symbol we use to write this is the absolute value bars. We call this cardinality. So the cardinality of the naturals is the same as the cardinality of the reals. We have a whole bunch of cardinalities for really popular sets. So these are the integers. This is like 0, 1, 2, 3, 4, kind of in the negative direction, so -1, -2, -3. This is the rationals. These are all the fractions you ever think of. I don't want to. It's kind of like we don't usually think of like orbitals necessarily as sets. If you could associate omega 1 to a set and omega to a set, you could biject between them, right? If we thought of omega as this tower of natural numbers that reaches an endpoint, and we thought of omega plus 1 as, well, omega with one thing on top and then a bunch of stuff on the bottom. Because bijections don't actually care about ordering, I can take this top element, send it to the bottom. I'll still have an infinite stack lying on top of that, and that kind of blurs the line between allowing us to make a bijection here. And so all of these guys, and I'm hand-waving over all the details, but every single one of these guys is going to be the same size or cardinality. It's weird to talk about orbitals that way. But is that all right so far? I know that's a weird idea. Any questions? Okay. Cantor, I don't actually know how to say his first name, Georg or whatever, Gregor, there you go. This guy lived from 1845 to 1918, so this was around the late 1800s. He wanted to address the following question. We found these really nice bijections between all these sets. So what's the next set you might wonder about if you're familiar with math notation? Is the natural numbers less than or equal to the real numbers? So the real numbers is your number line, right? There are things like the rationals which have nice fraction representations, but in the real number line you get things like pi, square root of 2, a whole bunch of extra stuff. And if you really wanted to answer this question, are these two sets the exact same? The way he went off to show that this is actually a strict inequality is he used an argument called diagonalization. First thing we gotta do is we can use the function arctangent to biject the real line into 0, 1. So I'm going to hopefully have you agree the size of the real line and the size of the interval between 0 and 1 are the same. So I'm going to try and show that this set has a strictly greater cardinality than this set. The way we go about this, we're going to try and just assume that some bijection does exist. So I will list my natural numbers. 4. So I will start at 1 and break convention, but 1, 2, 3, 4, so on. And in these columns, I'm just going to randomly list out real numbers. Does anyone want to be a guinea pig for giving random numbers? Go, Hazel.
6, 2, 8.
Okay, hold on. 6, 2, 8. Okay.
2, 1, 8.
Okay, that's enough. All right. What's going next? Liam.
4, 5, 1, 9, 7, 3, 2.
Okay. What's going next?
Go ahead.
1, 2, 3, 4, 5, 6.
Ooh, contrarian. How about 8, 6, 7, 5, 3, and 9? One more? Good.
3, 3, 3, 3,
Okay,
7.
all right. 7?
7.
All right, 7 at the end. Okay, so, and keep in mind, all of these are infinite. I've been trying to request enough time to list infinite numbers, but that wasn't approved. So, what we'll do here is we're going to go to each number in my list, and for the first number in the first place, we're going to change it. So we'll change the 6 to a 7. I'm going to look at my second number in the second place. I'll change my 5 to a 6. In the third number in the third place, I'll change my 3 to a 4. So we're just adding by 1. Fourth number, fourth place, I get a 6. Fifth number, fifth place, right, I get an 8. And I will keep doing this forever. And for 9s, I can just flip back to 0. So notice what's happened here. Let's ask the question. Does this number show up in my list? I've assumed that I could make a bijection by pairing every natural number with some real number here. But where does this number show up? Well, the answer is nowhere. Is this the same as the 50th number? Well, no, it would be different in the 50th place. Is this the same as the millionth number? No, it's different in the millionth place. And no matter what we try and do, even if I somehow use my, stacking at the bottom trick, I can always find another real number that escapes this bijection. And so we can now call this like a theorem. This is a statement will never be true. The real line is strictly larger than natural numbers. Still good so far. I know that was, yeah.
You're assuming that all numbers have a unique decimal expansion.
Yeah, I am. Okay.
Hand, Clark.
So, in general, we'll refer to numbers that share cardinality with the naturals as countable, because in a sense I can go down and count them. We'll call everything else uncountable. If there's an infinity greater than natural, we'll call it uncountable. And so, since my ordinals keep going on forever and ever and ever, I'm moving through all these countables. I don't know at what point, it's going to be a while, but at some point, there will eventually show up an ordinal that I can associate with an uncountable set. This ordinal we will give the name omega 1. And let me grab my eraser.
Wait, sorry, could you repeat what omega
Yeah,
1
yeah.
is?
Oh, sorry, say again?
Could you just re-describe what omega 1 is?
Yeah, so all of these ordinals here are going to be like countable in a sense. I can biject between them. At some point, since I've shown that this guy, which represents all of our countable sets, there's some object with a, infinity, we'll call it cardinality, I'll give you the word, right? Cardinality greater than the countables. At some point, all of my countable ordinals will eventually approach some limit, which is a ordinal that's associated with an infinity, which is uncountable. That's a lot of words. You get that right? So like, our first uncountable infinity shows up at some point, and we'll call it omega 1. Are we okay with that idea? Okay.
Is omega 1 equal to the cardinality of the reals?
That's a great question. I'll talk about that like the whole time. Right, okay, so spoiler alert, we can play this game with this kind of approaching limit here. There are a lot of different infinities, or cardinalities, right? So I've given you ordinals. These guys, this guy, and a whole lot more. I can keep playing this game. These are cardinals. So the cardinals start listing an increasing sequence where each one of the, each next cardinal can't biject the one before it. So if you want to think of like size of infinity, here's our smallest infinity. This guy's countable, so obviously, countable. This next guy is the first smallest uncountable set, so uncountable. Everything after that's also uncountable, but omega 2 is even bigger, omega 3 is even bigger, so on and so on and so on. Okay, so let's, for a moment, address Eden's question, right? What's the cardinality of the real line? Oh, before I do that, super quickly, let me introduce a theorem. So, I guess before I do that, I should give you a notation. Do you recall when I gave you the power set axiom? So the power set axiom tells you that for any set, there exists another set which contains all the subsets of that set. So, I don't know if I have one or two different ways of saying that, but like, if I look inside of a set, right, so the natural numbers, the even numbers are a subset of the natural numbers. The odd numbers, powers of 2, power of 3. Those are all subsets. So there must exist some set which contains all of those subsets individually as their own objects, right? We're going to take this next theorem on faith. And by the way, when we write this kind of cursive P, that represents the power set. So the power set of the natural numbers is equal to the real line. So I'm going to sheet that at the very least. As an exercise to the reader, as an exercise to the reader, you can kind of imagine like return back to our numbers between 0 and 1. If you expanded them into binary, you could sort of imagine that each binary number is counting up your natural numbers. So 1, 2, 3, 4, 5, 6, so on. Take every single, all different binary numbers, and then if a 0 shows up, reject that as in the subset. If a 1 shows up, accept it in the subset. So this string would describe the subset of 2, 3, 5, 6, 9, 10, and so on and so forth. And this is also why you'll sometimes see notation like this. Well, I'll use just random object A. The power set of a set A is the same as 2 to the power of A. What this is actually telling us is it's the set of all functions from A into 2. It's just laying out this argument. I know I'm hand-waving a lot here, but can we just accept this notation for now? Okay. And then the power set of the naturals is the real line. Okay, so finally let's go ahead and address Eden's question, right? So we know that I need to introduce one more theorem. I'm so sorry. Maybe theorem number 2. Well, this goes almost hand in hand with that theorem right there, but it's also true that for any set, the power set is greater than the original set. So this theorem, this result, we know at least that the real line is greater than the natural numbers. Yeah, go ahead.
The power set, but what about the sets that we use to define like numbers? Or maybe I'm getting that wrong.
Be more specific?
Like when we did the set notation for 2,
Sure.
I thought the whole point was that like it had all of the possible combinations of like 1 and 0, and like it has.
It is true that 2 is the power set of 1.
2 is the power set of 1.
But that pattern breaks because 3 is not the power set of 2. I'll actually return to that later in the talk, so maybe hang tight for a moment and see if I address that question. Okay, so here's our result we're trying to show. I have omega, I've got the power set of n. Where does this land? We know that n matches up with this guy, right? All I know is that it's strictly greater. I don't necessarily know which next infinity this guy lands. It could land at omega 1. It could land at omega 3. It could land over here, right? Our question is, where does that go? Where does the power set of the natural numbers land in our hierarchy of increasing sides of infinity? Does that sound okay as a weird question to address? Mm-hmm. So this problem is actually called the Continuum Hypothesis. There's 2 U's, whatever. Right? Cantor said this. He thought that the real line was omega 1. He would agree with your proposition, right? He thinks that the cardinality of the real line, with the power set of the natural numbers, lands right here. You've got the smallest infinity, the natural numbers. You've got the next smallest infinity, that's the real numbers. He tried really, really hard to prove this, and then he died. And everything. As it turns out, this question is very, very strange. For the reasons that our basic assumptions that make math work are not actually strong enough to make a decision on this. So all the axioms we just went through the slideshow on, those axioms cannot actually give you an answer to that question. I'm going to attempt to show you why that's true for the rest of the talk. Is there like any questions on that? I know that was like a lot. This is like part one done. I'm going to move to part two to talk now, so we get anything out of the way. Okay. I'm going to briefly tell you about models. So when we work with axioms, we also work within a model. So the axioms tell you like the rules. The model gives you an interpretation of those rules. What our goal will be is that if I can get one model where all my axioms turn out true, and the statement I'm looking for, the continuum hypothesis, is also true, and if I can get another model where all my axioms are true, but the continuum hypothesis is false, I will have two interpretations of my axioms. One that gives me a true answer, one that gives me a false answer, and we'll then call that statement independent. I'm going to give you an example from geometry to hopefully make this a bit clearer. Maybe you're familiar with this guy Euclid. He kind of wrote down axioms of geometry. I'm not going to put them on screen, but I'll read them to you, and you can tell me if you notice anything that's weird. Okay, axiom number one, these are things that should be true in geometry. That we can draw a straight line from any point to any point. Okay, pretty reasonable. We can produce a finite straight, that should be infinite straight line continuously in a straight line. Okay, yeah, pretty reasonable. To describe a circle with any center and any distance, pretty reasonable. That all right angles are equal to one another, also pretty reasonable. Now for the kicker. That if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the straight lines, if produced indefinitely, will meet on that side which the angles are less than those two right angles. People look at that and are like, what the hell? Why is that so complicated? Why were your first four axioms so nice and neat, and this last one is like actually insane? People worked on this problem for a very, very long time. The essential argument was, we want to know, can we use those first couple of axioms to derive the complicated one? And that complicated one is called the parallel postulate. Parallel postulate. Essentially, that's very complicated. It means like straight line, or parallel lines don't ever intersect. So people worked very, very hard to see if those basic axioms could describe the parallel postulate. The answer is they can't. They can't say yes, they can't say no. We're kind of all familiar with Euclidean geometry, space, right? How you graph lines in high school. If I draw two parallel lines here, they won't ever intersect. This is a model of geometry in the sense that my first four propositions reasonably hold, right? Everything is true. I can make circles, straight lines. Then what people started doing is they did geometry on spheres. As it turns out, if you think like lines of latitude, I could have two lines which reasonably approximate parallel lines, but at some point, due to the curvature of my globe or my sphere, they'll eventually intersect. And so the parallel postulate is false here, but true here, so it's independent. Those first four propositions aren't actually strong enough to make a decision. So I'm going to attempt to do the exact same thing we did there with the continuum hypothesis, show that my axioms aren't strong enough to make a decision. Good so far? All right. Super, super quickly, because I know I'm taking a while here. Can I erase my ordinal picture here? Is this okay? Okay. I want to talk briefly about the standard model of set theory looks like. So this is thanks to von Neumann. We start by building a hierarchy. So V0 is going to be our empty set. At each next stage, we take the power set of the set that came before us. So V1 is the power set of V0, which is the set of the empty set. V2, power set of V1, set, set. This looks a lot like the natural numbers. This diverges starting at 3. The power set of V2 is not the number 3. I'm not going to write that down because I need to save time. But essentially, we keep going up in this hierarchy. We keep taking power sets and power sets and power sets. Eventually, we can reasonably assume that V omega shows up at some point. We'll get a V omega plus 1, omega plus 2, 2. We can keep going. We get a V omega plus omega. I mean, we can keep going and going and going. And the reason we use this letter V is because there's kind of a mental image of this universe where the spine are the ordinals, and at different levels, we get increasing bits of information about the universe. So we'll have like the lower levels, we'll eventually hit V omega, we'll hit V omega plus omega, and even V omega 1 is out there somewhere. We can keep going. Some brief fun facts. This grows so incredibly fast and gives you so much information very, very quickly. V omega is enough to model like number theory. It's kind of finite to like countable mathematics. V omega plus 1 will be your first uncountable stage because V omega, well, the cardinality of V omega is countable, but the cardinality of V omega plus 1 is uncountable. V omega plus 2 is generally enough to do real analysis, all that cool stuff. 99% of mathematics you can do before V omega plus omega. That's just enough information. Of course, set theorists are greedy. We need everything, right? So we will keep going. We'll define this really, really weird-looking object. The bold V, which will be the union of all V alphas. I'm short on time. This is not a set. You get some. This is too big to be a set in a really weird sense. You get some like self-contradicting ideas when you try and call that guy a set. Because if V is a set of all sets, does it contain itself? If it was a set, could I take the power set of it? You get some weird results. But essentially speaking, any proof, any theorem you may want to do, there will show up some V beta for a beta large enough that you can do your proof. I'll also briefly state that sometimes, and this is bad notation incoming, okay, so don't go to like blossoming set theorists and write this down, okay? If I wrote something like this, okay, this is false, this is not true, but there's a reasonable assumption, you know, because a model can't prove its inconsistency, for those who know Gödel, that's for you. But we can't actually produce an entire model of ZFC, but there's kind of two options. You could either look at your proof ahead of time, say, I'm using this finite number of axioms to derive this theorem. I'm just going to use those axioms, find a V beta that's strong enough to show those axioms. Or you can just lazily assume this, is kind of what I say. Look at what axioms you did use at the end, then pick those out, and then say, I have a higher, you know, so wrong, this is wrong, but I'll put it in quotes because we can reasonably make this assumption. Am I still good so far? Oh, is there a question back there, or? No, okay. All right, so our goal number 1, let's produce a model in which the continuum hypothesis is true. We're gonna try and do this very, very fast. This is Gödel's L. It's called the constructible universe sometimes. We define this new term for a set A, SP of A. I have to kind of hand wave this definition here, but it is sets, or I should say subsets of A, specifiable from A, or just from the structure we're working with, like from the set theory, right? Essentially, the specifiable subsets of A is kind of like a much weaker version of the power set. I have a countable logical system And so if I'm jumping to these uncountable levels immediately, that's a little too fast in a sense. What we'll do is we'll look at all the sets we have and think, what do we absolutely have to put in? Like, what can we say for certain must come next, and build subsets from there. So like the natural numbers, you can pretty clearly define the even numbers, and that's pretty nice. But there might be some weird subsets thrown in there that are more mysterious. The way that Gödel builds his universe of L is that, and this might actually be convenient to kind of do over here, but we start with L0, which is still the empty set. At each stage, so the next stage in L are the specifiable subsets of the set that came before it. So we're throwing in only the sets we have information on at that point. We'll keep climbing and climbing and climbing. We get to L omega. At this point, we actually have this. So both of these models can reasonably define our finite set theory. Because everything finite we can reasonably define. Where these guys separate is that v omega plus 1 immediately jumps to being uncountable, because this guy is countable. I take the power set of a countable, I jump to uncountability. L omega plus 1 is only adding very nice subsets of L omega. And so this guy is still countable, as I said, the other natural numbers. So we're still countable by this stage. We can keep going, you know, omega plus some alpha, right? Keep building, keep building, keep building. A theorem from Gödel, which again I'm not going to prove for you. Any subset of n shows up at some L alpha or alpha before omega 1. So any subset of the natural numbers that I might want to define will show up at some stage L alpha before omega 1. Take me on faith for that, because what's going to happen here is that by the time we reach L omega 1, because that does exist, we've essentially defined all the subsets of the real line, right? What is the cardinality of all the subsets of the real line? Or the natural numbers, I'm sorry. We've defined all the subsets of the natural numbers.
Which is the power set for that.
Is the power set of the natural numbers. So this guy is, is uncountable, right? In fact, it's the smallest uncountable set, so omega 1. If we took the power set of the real line, what object does that grant us? Sorry, I'm mixing up real line and natural numbers. We take the power set of the natural numbers, what object does that grant us? The real line. If the cardinality of my universe is omega 1, what does that also grant us?
Equals.
What must the cardinality of the real line be at this point? It must be omega 1.
Yeah.
So in L, the real line is omega 1. So here's our model of set theory where that holds true. Are we okay with that so far? Okay, now finally, I know I'm running late. If you guys have to go, don't let me push you up. Now for the exciting stuff. How do we use forcing to build a model of set theory where the continuum is false? Okay, first assumption. We're going to start with a model of ZFC. Remember, a lazy assumption. And I want M to have two very nice properties. One, I want it to be transitive. This just means that if A is a member of B and B is a member of C, then A is a member of C. Things transition very nicely. My second property here is that I want M to be countable. Does anyone see a problem with this?
Yeah. How are you going to do proofs that require uncountable stuff if you have only m, which is countable.
You're my lifesaver. Thank you. Yes. How do we do that? How do I take a countable model if I know ZFC models uncountable sets? This is the Skolem paradox. I say paradox in quotes because it's not a paradox. All that we need to think about here is what is the requirement to show that something's uncountable? To show that it's uncountable. No bijection can exist to a countable set. So all that has to happen is that within M, it has an object that looks like omega 1, but from the perspective of M, I can never biject from omega 1 down to omega. And the way that we actually represent objects, we call it relativized to M, is by hanging an M on the top. So in M, there lives these objects, omega M, omega 1M. No bijection between these ever exists. But I can see from the outside of my universe, that guy is, M thinks this guy is uncountable. I think it's countable. I know it's countable. So I'm looking from the outside. Is that a reasonable, workaround to my paradox here? Can we accept this idea that a countable model could represent uncountable sets?
By just making them non-biject.
Yeah, by just making my model in such a way that no bijection exists to a countable set.
Seems like you're cheating, but okay.
Okay. And so this notation holds in general. If I have any object alpha, the relativized version is alpha m. So it's just the object contextualized back to m. Okay. Finally, we can talk about forcing. Okay. So the whole idea goes as such. If I want to disprove the continuum hypothesis, I would have to show that the real line has a cardinality greater than omega 1. To do this, we're actually going to add objects to our model. So we're going to add information to it. We need to be very, very careful when we do this. If we kind of do this all willy-nilly, stuff can break very easily. So let me walk you through an easier example. Before I start adding real numbers to my model in mass, let's do a simpler example. So let's, we're going to add a single real number to our model. So my goal here, add one new real to M. Okay, so what we can do is we can kind of predict what this new real number might look like using a partial order. Don't worry too much about what a partial order is. I will draw a picture and it might make a lot more sense. So what could this new real number look like? Well, let's start with nothing. This is kind of the maximum element of my partial order. Let's start with the first number, right? My new real number can start with a 0. It can start with a 1. Its next element could be a 0, it could be a 1, and that would hold for both cases. Right, and this will keep extending and extending, and I'll kind of get this descent into this partial order where I'm describing different versions of what this real number might look like. And let's again think of binary expansions. So this is not a real number in digits 1 through 10. I'm using 0s and 1s to encode information of a new real number. And that's kind of weird. Is everybody okay with that for now? So different paths down this partial order are kind of building a different real number. So questions? Okay. The way that we order these partial orders is we go in the reverse direction. So we can compare elements and we'll go like this. So this is the largest element and they kind of get smaller, but we're comparing these in the sense of how much information they encode. So all we need to think is that the further down we go, the more information we get about what our new real number might look like. Make enough sense so far? Okay. Now what we want to do is we have this partial order which kind of infinitely descends and describes all these real numbers. We want a way of describing potential properties of this new real number that aren't too special. And the way we do this is with a dense set. All right, so I'll give you the definition of a dense set. So, oh, one more thing. The symbol we typically use to represent our partial orders is a bold P. So you see a bold P, that's my just name for this tree. Okay. Dense set is a subset of my partial order. There are two property rules. For every P in the partial order, so elements of my partial order I'm going to call conditions. So any condition within my partial order, there is some Q in the dense set such that Q is less than P. Okay, so let's pause for a moment and translate it to English. My dense set should describe some property that is not special enough that no matter where I find myself in my tree, right, if I'm kind of describing a real number, I'm taking a path down the partial order, no matter where I am, I can always look at the property described by my dense set and find my way into it. So I'm defining a new real number. Okay, I want to make my way into a dense set. I'm either already in it or some path down the tree can find my way into that dense set. Is that reasonable enough? Okay. And then the other thing we'll ascribe density to is for every condition of the dense set, conditions below it are also in the dense set. So dense sets kind of capture downward everything else. Okay, I'll run you through two examples real quick. Okay. The dense set of sequences of zeros and ones longer than 13. Is this dense? Yeah, why?
You're just gonna get there.
Yeah, you'll get there eventually, right? Either I'm already longer than 13, or my number is short enough, I just keep going down the path and I'll get a sequence longer than 13. How about another example? Sequences, which I know I'm butchering spelling, start with a 0. Is this guy dense? No. Why is this not dense? If I start with a 1, how could I ever hope to change information before me? You can only add information. I can't go back and change my mind later. So an example of a dense set, an example of a set which is not dense. Okay. How are we doing? I know I'm running long for a minute here. We're almost towards the end. Okay. Now, when we add our new real number, we really want to make sure that nothing breaks, okay? So, all of the different dense sets which we might find in our partial order are kind of describing these non-special properties. And so, definition, generic filter. I'll just leave it as generic. We'll say that G as a subset of the partial order is generic if for all dense sets D, the intersection of G and D is not empty. Okay, let's translate this into English now. A generic filter should intersect every dense set in your partial order, right? It's reasonable to expect that this is possible, okay? No matter where G starts, I can kind of look at the next dense set I want and find a way into it. Okay, look at the next dense set, find a way into that. The next one, find a way into that. We can construct this object which intersects all of our dense sets. And essentially, G is going to be this long path down the partial order which intersects all my dense sets. So I don't know what it might look like, but you know, it's going to be some way down this partial order, intersects all of my dense sets. Okay, here's a big theorem now. Let's actually show that we're defining new information. So I'm going to erase my example here to keep the definitions up. Let's define G as the big union of my generic filter. So all I'm doing here, imagine my generic as kind of working its way down the ordering. It's defining a longer and longer sequence of zeros and ones. And I want to show that this long sequence of zeros and ones defined by my generic is actually describing a new real number. Does my goal make sense here? Okay? I want to show that my generic gives you a new real. So I should be able to show that it's different from everything in my old partial order. So I might claim that G is a function from omega into 0, 1 is a new real number. All right, so let's prove it, right? If I take some function in my partial order, right? So just think of like some function in my model, my partial order that defines a omega to 0, 1, right? All we're doing here, when I write these down, I'm just saying all my natural numbers, assign it a 0 or a 1. I can define this set D sub f, which I'll define just using English. The set of conditions which disagree with f somewhere. My question to you, would this be dense? If I have some function in my model, the set of conditions described by my partial order that disagree with f somewhere, is that dense? The answer is yes, because just think, right? If I'm a function and I'm taking some path down my partial order, just change directions, right? If your function is going one way, at any moment you want, just go the other way. And you now disagree with that function at some point, right? So if this is dense, and if my generic has to intersect every dense set, what does that say about G when compared to an arbitrary function? They must be different somewhere. So we pick a generic function, it has to be different from our generic. And so we have a new real number defined by the generic filter. Is that okay? Okay, I see some good nodding, all right? And by the way, what do I want to erase now? My generics intersect every dense set. Got it? Okay. So the other thing we'll call is the generic extension of M. We represent by mg, like this. All we need to think about this as is the smallest model of M that contains G as a set. So we're adding this new real number to our model. So when we take mg, we have a generic, we're adding that information into the new model. Good? Okay. All right. Keep going, I'm trying to be fast here, I'm so sorry. It's reasonable now that mg might look a bit mysterious, right? We kind of added this information, but what is going on there? So we want a way to describe what's happening in mg, but we're kind of limited to what we know about m, right? So, definition. A p-name. All right, so a p-name looks like this. Use dot notation. X dot is a name. If for any y dot comma p in the name, we have that y is a name and p is in my partial order. The takeaway here is that names are built out of other names. So names a lot of times will look really complex, and we build them with this kind of recursion. But what I kind of think of is like, if there's some object in mg that I want to describe, before I'm gifted my generic extension, I don't necessarily know what my new object will look like. So I use a name to collect up all of the things that might give me an object, and then I wait for my generic to come and kind of make a decision. So the names are just a big collection of things that describe objects. All you need to really know is names describe objects in MG, but they live in M. So names live in M, describe MG. Alright? Okay. I will keep my partial order up just because it's kind of nice. Then one more thing we can do is we can evaluate. So if I have a name and I want to evaluate it for G, I have a big definition here, but I'll spare you, I won't write it. What the evaluation of a name is, right? Imagine your name as a big collection of objects that describe a certain object. I should say a big collection of names that describe an object. Each of those names have conditions buried in them, right? So when I take the evaluation, what I do is I look at what parts of that name actually got hit by my generic filter. So my generic, I don't necessarily know what it looks like, it's kind of mysterious, but that generic will come along, it'll make a decision, it'll give me a new real number. I can look inside any name and look and see what components of that name were decided by the generic filter. So names in M are kind of these abstract objects. Our generic comes down like a bolt of lightning, makes a decision. These names collapse down into something that's definable. And we will write X over G to be the evaluation of X dot by G, my generic. Is that too hand wavy? Is that good enough for now? Okay. One more thing I'll give you. I'm just going to write this down because I might want it. Well, you know what? I'll do it on the fly later. Okay. I'm going to give you a theorem and I'm not going to prove it. Because I'm low on time. I'm past time. These two properties are true. Our original model is a subset of the new one, and the generic shows up as an object in the extended model. The way you would do that is you would just make names for them. I can create a name for anything in M really nicely. I can create a name for G. Don't worry about how we do that, but I can make names for these objects, and so my generic can decide these objects. Let me talk super briefly about the big theorem here. So, I'll get rid of evaluation. That's not that large. The forcing theorem. This is the big one. So I'm going to write a gross looking math sentence down, then we'll talk about what it means. Okay, so this was the big theorem. There's a lot of symbols up here that don't make sense, but I can guarantee that there's one symbol up here that even if you can make sense of this, doesn't make sense to you either. What symbol is that?
Is the phenomenon?
No. This guy right here. What does this mean? Okay, with a lot of hand waving. What Cohen was doing when he made forcing is he defined this relation. Right? I want to write part of this here. We can just describe this as forces. Read this as forces. It's built in a really complicated way, but essentially the way in which we construct it gives us a reasonable interpretation of this. So let me talk about this for a moment, I'll come back to here. What this tells me is that my extended model, so the model after I add a new real number, will reflect truth in a statement. So a name X after the evaluation Any property it might have can be reflected true in my extended model. So my extended model can look at an object and a property that object might have and say, yeah, this is true, this object, this property is true. It will only say that something is true if some element of my generic forced that to be true by a name for that object in the original partial order. So I can look at my partial order, I can look at a whole bunch of names, I can see something in my generic that forced that thing to happen. If something from my generic forced that to happen, my extended model will say that that was actually true. I'm trying to think of a good way to describe this without going too mathy. Essentially, what this theorem gives us, without going into the deep end, we were really careful when we added new information. We found our dense sets, we did our generic. We were so careful, in fact, that we can actually predict outcomes in the extended model just by looking in the ground model. We can look in M, see things using our generic, and predict outcomes in the extension. This is kind of what this theorem grants us. I know that's really, really out there, but that's like the second to last thing I need before I show you the continuous false. So I know I've done a lot. I'm almost done. I promise. Okay. All right.
There's donuts.
Yeah, there's donuts, right? Exactly. Okay. So a reasonable thing that I want to show, and I will just really tell you to take my word on this. What do we do with the geometry example? In both universes of geometry, they had to reasonably, model our assumption about geometry. So here's a theorem. My extended model satisfies ZFC. Again, lazily speaking, because it's kind of bad to say. Essentially, what I should be able to do is I should be able to define all my axioms using the names and the forcing theorem and all that. And it is constructed to be countable and transitive, which is really nice. So you get some axioms for free, you get extensionality for free, you get foundation for free. You can use names to build some of the simpler axioms. You can use names to get a union, right? So you take an object, construct a name, describe its union. You can get pairing really easily. I can give you this one. So we have two sets, x dot and y dot, well, two names really. I can make a new name, which looks like x dot, and I introduce this weird symbol 1, y dot, 1. All that this bold 1 means is this is the condition that's the maximum element. So no matter what decision the generic makes, this set will get these two objects excited. So I don't really know what this is until I take my generic. I don't really know what this is until I take my generic. But I know that this will have both in a minute. So there's your pairing axiom. You can define omega using names, get infinity, and you can do a lot of hard work to get replacement comprehension and choice. I don't want to do that hard work, so I'm not going to. All right. Now for my grand finale. As it turns out, all of this hard work we've done with dense sets, generics, partial orders, this actually holds for any partial order in general, or at least partial orders that are defined nicely based on more rules that I won't talk about. But we want to disprove the continuum. So we want to add a lot of real numbers to our model. In fact, I'm going to specifically add omega 2 in M, new reals to our model. So our partial order in this case is going to be this. And I'll write the gross formula first. So what this is are finite partial functions from omega 2 to omega into 0 and 1. So this is a bunch of functions that look like this, right? It'll take some input where alpha is in omega 2 and n is a natural number. And it sends that into either a 0 or a 1. So 0 for not a subset, 1 isn't a subset. And the way I imagine this is like a matrix. So we've got omega 2 down here, we've got omega, and we've got these columns extending upward. And every single box in this column will be either a 0 or a 1, right? Okay? So you might kind of be able to see where I'm going with this. I'm kind of constructing a bijection in a sense, right? I'm listing out all of my elements of omega 2. I'm taking functions from omega into 0, 1, which constructs subsets. So for this column of omega, that guy's not in the subset, that guy's in the subset, that guy's in the subset, not in the subset. I'm doing that for every single function of omega to 0, 1. Now we should just show that we can add this to our model and assume and all that great stuff. So these are finite partial functions. So these columns start out finite, but the farther I travel down the line with my generic, the more information I describe. So once I take my generic, these columns kind of extend to the infinite level and give us all the information we can want. Okay, super similar thing to what we did before. Define my function g as the big union of a generic filter. So g looks like a function from omega to m times omega. This is just saying pairs of alpha n, or alpha is omega, n is omega, and it's sending it into 0, 1. And I want to claim that g alpha n is not equal to g beta n for all alpha and n. So essentially, I can kind of just describe this with words. What we want to know is that if I pick out any two columns in this matrix, they disagree somewhere, right? So if I pick alpha, beta, I look at the functions from omega to 0, 1 they define, I should be able to find some spot where they're different. They have to be different because I'm defining unique new real numbers, right? Here are my real numbers I'm adding, right? So I would want to assume that every real number is unique. The way that we do this is by essentially using a density property, right? Really similarly to how I showed you that the adding one real number was unique to all other functions, what we could do is any condition, right? If you just show any condition P, well, P must be finite, so it's giving you a finite amount of information about these two functions G that we chose. I can extend it into a new condition, and it will look like this. So start with P, then go to P joined up with, this is going to look really close, but I'll write it down just for goodness sake, I guess. So what this gives me is this is a condition. I can find some way down my partial order where my condition makes a decision about g of alpha and n, says it's a 0. My condition about g beta and n is a 1. As it turns out, these conditions are dense. So our generic has to intersect this somewhere. So essentially, for any two columns of my matrix, I can keep going down my partial order, following my generic, and at some point I have to find a spot where those two functions are different. Because, I've listed out all of the elements of omega 2. I've taken, binary copies of real numbers or subsets of omega, however you want to think about it. And I have omega 2 unique versions of that. What does that mean? I have omega 2, at least omega 2, new real numbers in this model. So in MG, in our case, this is the implies thing. This implies that CH will say that the real line is greater than omega 2. And with a little more complicated math that I'm not going to cover, we can actually roll this down to an equal sign. So in our new partial order, we have forced that the real line must have omega 2 unique real numbers. And there you go, right? There is, we had our universe L, Gödel's L, where the continuum was omega 1. I used my forcing method to show you that the continuum is omega 2. I have a model of set theory that gives you a continuum being true, a model of set theory that gives you a continuum being false, and so it's independent. So from here, really, you get to choose, right? You can either decide to accept the continuum, add that as an axiom, or you can decide to reject it. And you can see what sorts of cool math goes on from there. I remember when I first found out that like ZFC was incomplete and there's like theorems will never prove, I was kind of like really butthurt about it. I had this like naive notion that no matter how hard I worked in math, I could just prove anything. But now I'm kind of happy. I think it's pretty cool that no matter how hard we work, there's always like statements that will escape our grasp. But that's all I've got. Thank you. I know I'm a lot past time.